Okay everybody, this is Dr. Pennington again. It's been a while since I made one of these videos, so hopefully what I'm going to say is going to make some sort of sense, alright? I want to talk to you guys a little bit about alcohols in synthesis. Now I have all this stuff written up here because these represent conversions that you guys have all seen before. You would have seen these in Organic 1. You can convert alkenes to alcohols and back, you can convert alkenes to alkynes and back, you can convert alkenes to alkanes. Can't go back in one step. You can convert alkenes to alkyl halides and back. You can also convert alkynes to ketones or aldehydes depending on where the alkyne is. What you haven't seen yet, and what we're going to go through at least to some degree now, is the fact you can go from ketones or aldehydes to alcohols and back. Right now we've seen these reduction reactions already from a ketone or an aldehyde to an alcohol. But we're also going to be seeing those that we can go the opposite way. We can go from an alcohol to a ketone or an aldehyde or a carboxylic acid depending on what oxidizing reagent you use. We have strong oxidizing agents like, for example, chromium oxide in sulfuric acid. You can also use potassium dichromate for this. This is a strong oxidizing agent that will oxidize an alcohol as far as it can go, a primary alcohol, all the way to a carboxylic acid. There's also pyridinium chlorochromate, which is a weaker oxidizing agent that will oxidize a primary alcohol just to an aldehyde. As far as secondary alcohols go, both these oxidize to ketones, will oxidize a secondary alcohol to a ketone because that's as far as they can go. Tertiary alcohols that already have 3 alkyl groups on the carbon can't be oxidized at all, so it doesn't matter whether it's strong or weak. Now I've also drawn these 6 down here. Anytime you're doing an interconversion, it's always useful to know which of the groups you're converting between, and these are the most common ones you guys are going to be seeing. So I've put these on each of the other synthesis reactions we're going to be going through today. So let's look at one. First one here, going from an alkyne to a, hopefully you guys can see that's a Markovnikov alcohol. Look at the number of carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's 6 carbons each time, so there's no need to worry about either a Grignard or an acetylate ion to form new carbon-carbon bonds. All we're doing right now is just interconverting functional groups, ultimately from an alkyne to a Markovnikov alcohol. So let's think about it. There's actually 2 different ways to go through this, and we're going to just focus on one of them right now. Okay. Now let's see. When you think about reactions we saw last semester, what functional groups did you remember you can make alcohols from? Because we only saw one. And the one we saw was from an alkene, if you remember. In other words, akin to conversion like that. Now, if you remember, this is a Markovnikov alcohol. There's 2 ways to do this. One is oxymercuration, demercuration, a 2-step process. The easier way, which is just 1 step, is literally water and sulfuric acid. This is usually just shown as H3O+, because H3O+ is what you get as the dominant species when you dissolve any strong acid in water. But what about from the alkyne to the alkene? There's only one way you saw for this, and that was addition of hydrogen, but you needed a catalyst that is poisoned and stops at the alkene stage, and that was the Lindlar's catalyst that I'm sure you guys remember. You don't need to know the structure of the Lindlar's catalyst, you just need to know the name. So that is a 2-step process, and this working backwards, this is what we call retrosynthetic analysis that I know you guys saw last semester. All right, so that's the conversion that we went through there. Now let's take a look at this one. This is a little bit more involved because if you see there's 1, 2, 3, 4 carbons here. 1, 2, 3, 4, 5, 6. So if you can see, we're adding 2 carbons. And this is going to use reactions that you saw last semester. All right? So let's think about it. What reactions do you guys know about how to form a compound like this? All right. Well, last semester, the one reaction that we would have focused on to add carbons to a chain was via acetylide ions, where you make a triple bond, a terminal triple bond, remove one of the hydrogens and add carbons that way. All right. But do you guys remember how we can do something like that? So how could we convert this double bond into a triple bond? Well, if you remember, it is not a one-step process. We have to open up the double bond first and then do a double elimination. If you remember, the first thing we had to do was to add bromine across the double bond to do that double elimination, to open up the double bond, and then we need the double elimination, NH2 minus twice will be fine to form that. Now here we have this extremely acidic hydrogen on the sp hybridized carbon, and if you remember, we can use a strong base. NH2 minus would work well for that, to make the acetylide ion. And then the question is, well, how many carbons are we adding in? Well, we're adding in 2. So first of all, we're going to use that NH2 minus, that strong base, to remove the hydrogen, to remove the terminal hydrogen. And then to add on the 2 carbons, we can't just say 2 carbons, we need a leaving group there as well, so bromine or chlorine or something would work fine. If you guys can see, that will give you a product that looks something like this. All right. Now, we cannot go from here to here in one step, but the only reaction you guys saw from these last semester was a reaction to give a carbonyl. All right, and in this case, it doesn't matter which way we attack. This is completely symmetrical, so we only get out one product, and the product we get out would look like this. It would go via an enol that would tautomerize to this ketone. All right. And if you remember, it actually doesn't matter whether we do the Markovnikov or the anti-Markovnikov approach here, because both will work. So let's just use the Markovnikov product, the Markovnikov approach, which is exactly the same as for an alkene hydrolysis. But if you remember, because alkynes are slightly less reactive, we need an extra catalyst there, the mercuric sulfate. Now, then the question is, well, how do we go from here to here? Well, this is a ketone, this is a secondary alcohol. If you remember, this is a reduction, and for that we need a reducing agent. Now, one option that would work just fine here, this would be a one-pot reduction. This would be sodium borohydride in methanol. Another option, though, it's a stronger reducing agent, and because for that reason it's a 2-step process, lithium aluminum hydride and water afterwards. So that could also work here. So either of these 2 sets of reagents would work for that reduction. All right. Now, last one here. What if I was to ask you to do this synthesis using a Grignard reaction? Now, we covered these in class. Now notice, if this is the only thing you have to start with and you have to form this, see how many carbons we have to begin with. We got 3 carbons here and we got 6 carbons here. So can you see it somehow means we've got to somehow sort of add 2 of these together. Now in a Grignard reaction, if you remember, to make an alcohol that requires us to have some sort of carbonyl and some sort of Grignard reagent. All right. So the question is, can we figure out, well, in the product here, which parts are going to come from the Grignard reagent, which parts are going to come from the carbonyl? All right. Well, can you see, we could essentially split this up into 2 separate 3-carbon units. All right. One here and one here. No prizes for guessing which part here is probably the one that originally was the carbonyl, and it's this one. This one would have originally been the Grignard reagent. So can you see then for this part here, that probably would have been this. That would be my Grignard reagent, right? And then the carbonyl here would probably be this. This would be an aldehyde in this case. So really the question is, how can I form both of these reagents from here? So let's focus on the Grignard reagent first, all right? If I want to make a Grignard reagent, does anybody remember the functional group I have to start from? Well, it's an alkyl halide, right? And in this case, it would be 1-bromopropane that I'd add magnesium to. And can you guys see that I can make 1-bromopropane from my starting alkene? If you remember, is this a Markovnikov or an anti-Markovnikov addition of HBr? Well, it's an anti-Markovnikov addition. So it's got to be the radical mechanism that you either use peroxides or hydrogen peroxide or whatever you want to do. So H2O2 would work, any peroxide will work. So this gives me my Grignard reagent, all right, from my starting alkene. But what about this guy? What can I do to make that? Well, the only reaction we've seen to make an aldehyde, apart from using an acetylidyne, but we don't want to add carbons here, the only way we've seen that so far is from a primary alcohol. But what if I want to make an aldehyde without going all the way to a carboxylic acid? Well, I need a relatively weak oxidizing agent, which PCC will work fine for that. And you guys can see that I can also make the primary alcohol I need from the starting alkene. This is another anti-Markovnikov addition. So the only way to make the anti-Markovnikov alcohol is by hydroboration oxidation. All right, and there we go. So the synthesis here would be, first I'll synthesize my, it doesn't really matter which one we do. First I'll synthesize this guy. So first I'll synthesize my Grignard reagent. So if I go down here and say, all right, here is my Grignard reagent. That looks like that. Using the two steps that I have listed there, which is these steps here. All right. Then I'm going to react that with my aldehyde. Now, in a Grignard reagent, this is always done in two steps, right? I have to add the Grignard reagent or the Grignard reagent to the carbonyl or the other way around, and the second step is always going to be water to protonate the ion. And what I would end up with is actually the product. So the only thing you want to make sure that you show here is that you show the formation of this as well, all right, using what we showed right here. So it doesn't really matter whether you put the aldehyde here or the Grignard reagent here, provided you put them both there and then you do H2O to protonate afterwards. That's a little bit about synthesis involving alcohols. All right, thank you.